So let's take a look. Let's see here. Let's change this around a little bit. Let's think about our zinc cell that we made in class. So if we take a look, we have zinc plus copper 2 yielding copper plus zinc 2 plus. And remember, these are the anodes and cathodes, the solid pieces of metal. And this is from the solution. The anions are considered to be what? I didn't draw them because they're considered to be spectators, right? Spectator ions. If we were to draw this, and I'm not going to use the nickel and iron, I'm just going to use the zinc one. And here we have our zinc solid. And but you know, like a light bulb or something there. And that's attached to our copper solid. And in here we would have zinc ions and sulfate's sulfate's a common one to use for that. Since it's a spectator, doesn't matter. And here is copper ions and sulfate ions as well. Then we used what Dylan did not think was a, what did you call it? Quality control would not have accepted my thing. Well, sometimes what they use is actually, it's filled with a salt, and it's like an actual tube. So it would actually be basically just a tube of solution in there. Or some type of porous thing that allows ions to go back and forth. That is the salt bridge. Bridge. So if we take a look here, zinc is going to zinc 2 plus. So what has it done? It has lost 2 electrons. So that means that zinc, right, oxidation is lost. This is the site of oxidation. What do we call the site of oxidation?
Anode.
Anode, good. And electrons always flow from the anode to the cathode. So the electron flow direction would be this. That would cause this light to light up, right? Put our little filament in there. And this would be called the cathode. In this salt bridge, we could have anything. Let's just use potassium nitrate. So as we look at this, the cation, the K plus, would try to travel towards the cathode, and the anion, the NO3 negative, would try to travel towards the anode. Meh? So we know that zinc is being oxidized and the copper 2 plus is being reduced. Remember, when you talk about these things, you identify the things on the reactive side, right? That's where it's all happening. So zinc is being oxidized, losing electrons. Copper 2 plus is being reduced, gaining 2 electrons. So if we were to find our E cell of this, we would take the reduced minus the oxidized. So if we find on this sheet right here, if we find the copper, that is, it's copper 2, so it's 0.34. and that is the reduced 0.34 volts minus the zinc, which is being oxidized. Where are you? Ah, here we go. Negative 0.76. Right? So this is the 2 plus, this is reduced minus the reduction potential of the oxidized is the way I do it. You could switch this and flip this, and then it would be plus here instead of that. Right? Just keep doing it the same way, whatever way you do it. Be consistent. 0.34 minus negative 0.76, and we get 110, right? 1.10. 1.10 volts. That's positive, so that we know that this right here will produce 1.10 volts. If we're using standards, standards is 1 molar of each of these solutions. What's going to happen to the zinc over time? Mass decrease. What's going to happen to the copper over time? Mass increase. How many volts would it take to reverse this whole process? We would have to use more than 1.10 volts to switch this around and have it go in the opposite direction.
Mr. Jackson, why won't the reaction, like why won't the current flow if there's no salt bridge?
If we break the salt bridge, then you remember your circuitry?
Yeah.
Yeah. We break the salt bridge, we don't have a complete circuit. So you would get a quick like a quick voltage, but then you don't have any once the electrons get over here, we don't have any potential difference anymore.
I got you. Thank you.
I don't get why the mass increases on the copper and decreases on the zinc.
So remember, we're taking electrons from the anode and giving them to the cathode. So as this gets more charged, copper 2 ions are going to adhere to this piece of metal. And as this loses electrons over here, zinc 2 plus ions will kind of be attracted by the water in there, the H2O in there, and they will be pulled off of this metal. As time goes on, more zinc is pulled off and more copper is added on until you would actually see an appreciative decrease or an appreciative increase. Is it cleared up?
Yeah, thanks.
You're welcome. Here are some more problems like that if you need extra work. I'm going to change this though into manganese dioxide, or what's called manganese 4 oxide, and that does not have that charge there. If you have issues finding these things, I'm going to put this document onto Canvas. This document right here basically is a more complete list. I gave you one part of this, which is the most simplified one. But I mean, you can look up on the internet. You can see that this one has more. There's also one in the back of your book. I don't remember the appendix number, but there's also one in the back of your book. But I'll put a link to this on there, or I don't know if it's faster for you to just look it up online versus go to that link on campus. Anytime that you needed these type of things, these would be given to you during a problem. Or it may actually be in like the equation sheet stuff. There's some more problems. It does have a little bit of different questions. It's like which one is voltaic and electrolytic. Remember, this is non-spontaneous and this is spontaneous. And the anode is always the point of oxidation. If you had questions about standards, arbitrary standards, we talked about that a little bit yesterday. Basically, we should understand that when we look at these atomic masses, the standard is based off of 1/12 of the mass of carbon-12, and that would give us hydrogen. We're under the assumption that a proton and neutron, the only difference is the positive charge. The proton, the masses are identical. In reality, it's almost a system of phase where if you're looking at a nucleus, this is like I shouldn't say reality, but the most common conceptualization of this now is that basically the neutrons and protons can like, switch in a sense. If charge is needed somewhere or whatnot, that charge moves to maybe a neutron that's non-charged, giving it the positive charge, which means that over here, then a proton that was charged is now. With the electrode standard potential, we base that off of hydrogen. It's been given a value of 0.00 volts, and that just means that fluorine fluoride has a 2.65 voltage better than the standard potential of hydrogen. So that's just how scientists basically make something. I mean, in reality, how do we know a proton is positively charged and an electron is negatively charged? And what if they called this one negative charge and this one is a positive charge? We know that opposites attract and stuff like that, so that's kind of just arbitrarily. That brings us back to Gibbs free energy. If we take a look here, we want to relate Gibbs free energy and voltage, cell potential. What is the Gibbs free energy of this guy right here? Is it positive or negative? It's negative if it is spontaneous, right? So Gibbs free energy here would be negative because we have a positive voltage going on. If we were looking at an electrolytic cell, then Gibbs free energy would be positive. Make sure we've got that down, delta G negative. We want to do that. Delta G negative is, let's do this. Let's do less than 1 or less than 0. Then it is spontaneous. If delta G is greater than 0, non-spontaneous. That might be the best way to do that. So here's the formula, and I'm so sorry if you printed that. If you have one of my printouts and it doesn't look this good, but delta G equals negative N F cell potential. F is Faraday's constant. I think Monk said yesterday you guys never had Faraday's constant, but it's 96,485 coulombs per mole of electrons. N is just like
What number on the AP test?
it's given to you. Yeah. Let me make sure I got it right here. Oh. Let me grab this sheet real quick just to make sure. 98% sure. I think I gave them out last semester, but there we go. Right there, Faraday's constant. It also gives you the 1 volt equals 1 joule per coulomb. So that right there means that we can change the cell potential into joules per coulomb. Volts, 1 volt equals 1 joule per 1 coulomb. And since this is in coulombs per mole, right? What we'll end up getting here is we will get our delta G in joules per mole, which works out. Delta G is also given in kilojoules per mole sometimes, but joules per mole is accepted as well. This is equal to the number of moles of electrons. Oh, and all of that is right there. So since the cell is valued spontaneous reaction, as we said, then delta G is going to be negative. And since cell potentials are calculated to be positive, the negative sign in the equation makes sure that it's going to work out. So if this is negative, then negative would make this positive, which would mean a non-spontaneous. Since for spontaneous cells, this is positive, negative times that positive is going to make this negative, which makes sense. So let's take our reaction from last time. Zinc solid plus copper 2+ aqueous yields for us the zinc 2+ plus copper aqueous. So if we take a look here, how many electrons are going to be given? How many moles of electrons for every 1 mole of this and every 1 mole of this? How many moles of electrons are going to be passed? 2. So N equals 2. We have Faraday's constant up here. And what was the cell potential of this?
1.1.
Thank you, 1.10 volts, which we could also call that 1.10 joules per coulomb. So if we have delta G equals negative NF standard, and remember, we were way below that for our battery that we made because my copper and my zinc were so corroded. That shows you that, you know, as time goes on, batteries are not going to be as efficient. We were way below that. So our delta G is equal to -2 96485 coulombs per mole. And then 1.10 joules per coulomb.
Why doesn't the mole and F cancel out with the
Here.
number of mole?
Oh, here,
Yeah.
let's use the number of it. We don't have an actual unit on that end. So basically, since this is per mole, we're basically just doubling this number. Does that make sense?
Yeah.
Yeah, and if there was 3 electrons, then we would be tripling this number. So that's all we're doing here. In reality, I should probably have that negative on this side. Let's do it. Let's put it up. Is divine anything anymore? Let's take that -2 times 96485 times 1.10. We get delta G equals -212,267 joules per mole. If we wanted to, we could do what? Divide that by 1,000 and convert it to kilojoules. Sometimes we do need to make sure that our delta G units match up with like our delta H units and other formulas. So that may be something that we would need to do. Just gonna make it into it. Last thing, I think we want to take a look at today before we do get into the next equation, which would be the last thing that, almost the last thing, I'm sorry. that we do on Tuesday is let's use that delta G to calculate the value of K. I'm going to do that down here. This is continued from the previous page. So if we take a look, we have the formula from our thermo unit, delta G, actually our equilibrium unit equals RT natural log of K. So we want to solve for K. And what do we expect K to be here? Greater than 1 or less than 1? The forward reaction favored or not?
What's spontaneous, right? So more than one.
Yeah, right. Because remember, K is equal to products over reactants, right? So that could be like one of those weird little like multiple choice questions or whatnot. So if we divide both of these sides by negative RT, we get the natural log of K equals a negative a delta G divided by RT. What do we need to do to get rid of the natural log? We take what to both sides? Right. So E and E. That gets that out. So we get this formula right here. K equals E to the negative delta G divided by RT. Let's assume this temperature is room temperature. So T will be 298 Kelvin, right? Remember that our R constant here is the R that deals with joules. 8 point, where are you? R, there we go. 8.314 joules per mole Kelvin. And our delta G is equal to, from the other page, negative 21267, right? Oh, nope, I'm missing one. 2122. 212267 joules per mole. So there are guys, oops, sorry, let me get them in there. There are guys for this formula. So now we just plug them in. E to the negative 21267 joules per mole divided by 8.314 joules per mole Kelvin. And here we have 298 Kelvin. So what all is going away? Unit-wise? Basically everything, right? Basically everything. K has pretty special units. Usually we don't bother with them. But like whenever we were doing if you recall, determining rates of reaction or whatnot, it depended on the order. So let's go ahead. I'm going to go do the negative. Actually, let's just get rid of the negative right away. 2.12267 divided by 8.314 divided by 298. It gives us that. And then we take e to that, and we get 1.008. I don't feel like that. I feel like it should be higher than that. Ah, there's our problem. Look at that. I snuck in a decimal place there. Now let's do that. There we go. 1.615 times 10 to the 37th. Is that pretty big? Yeah, right? It's huge. Makes sense because this is a spontaneous reaction. So K should be greater than 1. In this case, much greater than 1. Boom, boom. What would be the issue if we change concentrations? Because this is a 1 mole to 1 mole for the solutions, right? What would be the issue if we changed concentrations? Well, let's take a look. I'm going to put our formula back up here. Zinc plus copper 2 plus yields zinc 2 plus copper. If we make the K, what happens to zinc and copper? Are they in our K equation? No, solids become what in the K equation? 1. So they're ignored for that K equation. So all we're worried about are these two guys right here. So if K equals products over reactants, we know that this is spontaneous. So we know that our concentration of zinc 2 plus is going to be higher, which is going way higher in this case, which is going to make K way over 1. What if we adjust these concentrations? What if instead, let's say we use a higher concentration of the zinc 2 plus. Higher concentration of the zinc 2 plus, right? It's going to force the reaction in which direction? The reverse direction using Le Chatelier's principle. So we may get a voltage that's less than 1.10. What if we use a higher concentration of copper? It's going to increase the forward reaction. So we may get a higher voltage than 1.10. That 1.10 is for the standard voltage potential, keeping in mind that you're doing a 1 molar to 1 molar ratio. If we start messing with those ratios, we can actually adjust the voltage that we get from these batteries, these voltaic cells. It could be less than what we want, or I shouldn't say less than what we want. If we changed it, we wanted something, right? Less than what standard potential would be, or greater than the standard potential. And that actually brings us into what's known as the Nernst equation, which this is a decent version of it. That's what we will do on Tuesday. Monday will be 25 multiple choice questions up to acids and bases. That will be the asynchronous assignment. I will try to get that up before Monday, so maybe Saturday or Sunday, if you guys want to not deal with it on Monday. Right? Any questions from home viewers? Have a great day, home viewers. Any questions from the studio audience? Let me stop.